Hello, welcome to the CXL Consortium webinar. We will begin in 2 minutes. Hello, everyone. Welcome to the CXL webinar on advantages of CXL memory sharing for emerging applications. I will now hand it over to our panelists to begin the webinar.
I am Anil Godbole, co-chair of marketing work group at CXL Consortium, and I also work for Intel's Xeon product line, product planning and marketing group. Want to welcome you all today, and thank you for taking the time to attend today's webinar on advantages of CXL memory sharing for emerging applications. Today, I have with me panelists from a few CXL Consortium companies who offer products in this area. To save time, I will let them introduce themselves when it's their turn to present their material. But before we begin, I wanted to do a bit of level setting on this topic. If you remember, the memory pooling feature was introduced in CXL spec version 2.0. The graphic shows how multiple hosts could access a pool of memory below a CXL switch. Each host gets allocated a private memory area from the pool as shown by the color code. The memory pooling feature was introduced as a TCO savings play. The thinking was, rather than over-provision the memory needed for the worst case workload on a data center server node, one could do optimal provisioning and then have the host borrow more memory if needed. A demanding workload wanted more memory beyond what was allocated to it on the local node. Today, the cost of DRAM memory is a significant item on a server's BOM. And research has also shown that up to 25% of provisioned memory on the local node does not get used or is left stranded. Hence, if a data center which deploys tens of thousands of server nodes, the cost savings can be significant if memory pooling is deployed. And as the graphic shows, any memory pooling allocation to a host is typically done by the fabric manager shown on the little box on the right side, acting at the behest of a data center's orchestration layer. Later, in CXL spec version 3.0, the feature of memory sharing was introduced. As the graphic shows, any host can share a portion or fully, or or all of its memory, all of its private memory area with other hosts. For instance, in the graphic, a memory region on device number 4, which originally belonged to host number 2, is now being shared with host number 1. With the memory sharing feature, CXL pool memory is no more just a TCO savings play, but rather is a performance enhancement play, or is a performance enhancement feature. There are so many applications today, like distributed databases, big data analysis, where like the old map and reduce, and now today Apache Spark suite of tools, which can significantly benefit from this feature. In such applications, individual hosts typically divvy up a big chunk of data, crunch it, and then exchange the results over Ethernet networks. With memory sharing pool, the data is already co-located next to the individual host. And so one can simply exchange the data by passing pointers rather than shuffle it over some network like Ethernet or InfiniBand, and thereby reduce latency significantly and improving performance. And then for enabling the memory sharing under the hood, meaning no software or OS involvement, CXL 3.0 spec also introduced the concept of hardware-based mechanism of back invalidating. For instance, if host 1 wants to share a region which originally belonged to host 2, it requests the memory device holding host 2's memory, and then the device then sends a back invalidate command to host 2, which will then take the necessary actions to relinquish the ownership of that memory. As you know, CXL 3.0 was relatively recently introduced, and our member companies are developing hardware devices are working to bring these devices to the market. In today's webinar, we will see how using CXL 2.0 devices and switches, users can implement memory pooling and sharing using software-based coherency techniques. In today's webinar, the panelist companies will present how they deploy this technique to enable some exciting applications. With that, I will hand over to our first presentation, which is from UnfabriX.
Thank you very much, Anil. This is Oren from UnfabriX. I'm looking after business development. And UnfabriX developed memory over fabrics. To our first slide, I will describe what UnfabriX is doing in high level, and then we'll deep dive into the details. UnfabriX design smart memory fabrics. It means that we are able to connect multiple hosts to multiple resources. This is serving the AI market, HPC, in-memory database, and variety of use case. Today, I will present one of the use case in algo trading. We are the first company to provide software-defined memory. It means that everything in our system is fully programmable. It means dynamic allocation, implementing latency, displacement, and other features that we'll discuss in more details. We are providing highest bandwidth because we are able to connect multiple links to the same host. And we provide the capacity on demand. As I described before, we have both GUI and API that can control the capacity. Everything is open in our system, and we are based on CXL, both CXL 1 and CXL 2.0. When we're looking at the system, you can see the system on the right-hand side. This graphics shows a nice animation of pooling mode. Pooling mode means that every element, every host in the system can access its memory in the memory pool, separated by the max memory. Max memory is the name of the product. The system is star-based. It means that each link is separate and there is no noisy neighbor effects. The system today support up to 32 tera. Those can be both in sharing or pooling mode that we'll describe in the next slide. System is 2U and populated with DIMMs. Those can be DDR4, DDR5. It can be CXL E3S modules or any other type of memory. Looking at the sharing mode, in this slide, we can see three types of systems. So first of all, on the right-hand side, this is pool mode. In a pool mode, as I described before, each host can access a different memory space. Those are assigned in the graphics by different colors. Each system connects directly to the memory pool, and it's got its own memory space. In the middle and the left, we can see sharing mode. The left one is sharing mode number one. We can see single server that actually generate the data. And this is a very interesting use case that I'll describe in the next slide. In this case, one server produce all the data and all the other systems consume the same data. Sharing mode number two is actually all the servers approach the same memory space. All of them generate data and all of the servers consume the data. On the left-hand side, this is a simple mechanism, but it's actually got many use cases. So it's interesting to see that actually the simple mode of sharing is the more dominant one, at least in our system. More interesting one, and I expected this question at the end, that can we operate in both pooling mode and sharing mode together? And the answer is yes. So everything that you can see now in the slide can all work concurrently. It means that node number 1 and 2 can share the memory. Node 4 and 5 can work in sharing mode number 2, and all the rest of the node can work in pooling mode, and they can do it simultaneously. It means that node number 1 can do sharing with node number 2, and at the same time also use the pool mode. It means that it's got a different address space for host number 1. Moving to the next slide, we can see now a use case, which is actually make it more visible. So on the graphics, you can see that we have a system, the max memory that contain all the memory, and it's distributing all the data into the different nodes. In each node, there are multiple GPUs, and the CPU actually distribute the data into the GPUs. When those are connected using PCIe, the memory pool can actually then drive all the data directly to the GPUs. In the algo trading market, there are two use cases. One online, which is example number 1, and offline, which is number 2. In online, there is market positions. Market positions, it means that all the data from the stock exchange is being managed in the memory pool. All the hosts implement different algorithms, and each of the hosts can manage this data separately. It means that they consume the direct data from the market. It's being updated to the memory, and by that we are able to implement it through multiple systems without copying data. It means that we don't need fast storage system to distribute the data and copy the data multiple times. Second one is historical data. In each algo trading company, they are experimenting with new algorithms. There are many algorithms. They can maybe create algorithm based on the weather, based on the number of days on the week, which doesn't change. It's always 7. But the idea is that historical data create opportunity to test new algorithms. And the faster you are testing the algorithm, the more accuracy you are getting through the system. So bottom line, implementing the same data in the memory pool and running multiple testing at the same time through the same data can actually make faster decision which algorithm to implement for their next trading system. So bottom line, memory sharing technology create opportunity to make faster decisions in algo trading algorithm, reduce the latency because we don't use performance storage, it means that we are actually 100 times faster than any performance storage that you can find in the market. We are not Ethernet based, we are not copying the data. Everything is actually moving pointers between the host and the memory pool. This is an amazing opportunity for the algo trading market using the memory sharing. But more interesting is actually the TCO model. The TCO model shows that, for example, on the left-hand side, we can see each system have 4 terabytes. Those data being copied from the storage into each one of the hosts, and the same application that we discussed before are actually implemented on those multiple hosts while data is being copied. So overall, we can see on the left-hand side that we have 16 servers, each one with a dual socket, and each one is implemented with 4 tera. All the data is being replicated, so total we have 64 terabyte of data. 64 tera cost about $600K. On the right-hand side, what we can see is actually the same 16 servers, but each one is implemented with 256 gigabyte. And we have 4 tera in the memory pool. The memory pool is in sharing mode. It means that all the servers can see the same 4 tera. It means that all the systems have the same data, and we are implementing actually 256 multiplied by 16. It's 4 tera, and 4 tera in the memory pool. Total of 8 tera in the system, cost about 16K. Overall, it means that we can save about $500,000 just by implementing for algo trading type of workload, the memory pool in a sharing mode. So this is an amazing result. It's create cost reduction both by reducing the amount of memory, reducing the power, and actually the system is being dynamically managed, so we can use it also for memory pooling. Next slide is about the future. The future is actually having multiple memory pools working in both pooling mode and sharing mode across multiple systems. Those can be seen by the red dots that are implemented both. You can see multiple data moving to multiple hosts, or each one can use a pooling mode into each one of the max memory. So bottom line, this create opportunity to build multiple racks, not just 8 systems, but we can build multiple systems connected to multiple max memories. And if you would like to see us, we will be at ISC Supercomputing in Hamburg next week, and the AI Infra Supercomputing 25, and at the FMS. Come and meet us. And I'll give the stage to XConn. JP, stage is yours.
Thank you, Oren. Hey, good morning, everyone. My name is JP Chen. So I'm the Senior VP at XConn Technology, in charge of the CXL switch and the CXL product line. So just a very short introduction to who we are. So XConn, I think if you are with the CXL Consortium, you already learned our name. So XConn Technology is a startup company based in Silicon Valley. We make CXL switches, PCIe switches, and all the connectivity switches for the AI computing and the data center computing. So our product is a switch, and we are the world first. We have the world first CXL 2.0 called XC50256, and which is also a PCIe Gen 5 switch. So this switch is in production right now. Okay, so the switch is, as you can see from the part number, it has total 256 lanes, making it the largest lane count switch in the market today. The total switching capacity is a total 2 terabyte per second. And because of this design requirement to serve the CXL memory and the AI computing, we have made the switch to have the lowest port-to-port latency and the lowest power consumption per port. Also, the switch has a larger radix, make it ideal for some of the larger AI system designs. So if you have 8 GPUs or a number of NIC cards, that make a lot of sense. And if you want to build a very large CXL memory pool, let's say 16 terabyte, up to 100 terabyte, that also makes sense to have a very large radix switch. So our switch have been brought up from the past 2-3 years. We've been working with the ecosystem partners, processors, memories, and we make it switch be able to do memory expansion, pooling, and sharing. So the product is in the shipping production stage at this point. So just to give you some example of what our customer have built up using our switch. So on the left upper side is a switch chassis that built by the H3 platform. So this chassis has a total 24 the front E3.S port, which you can plug in all the Micron, Samsung, or Hynix E3.S card or other from Smart Modular, so that switch can make up to, I think, by roughly 6 terabyte or even more with a half terabyte E3.S. So the switch, so this box also connect to 4 hosts or up to 8 hosts. On the left bottom side is a box, the chassis made by Liquid, and Liquid use a add-in card inside the chassis. So this chassis has a total capacity of 10 terabyte, and this chassis coupled with a top-of-rack CXL switch can make an even larger memory pool up to 100 terabyte. And the upper right is a Samsung called CMMB. Samsung have been pioneering CXL technology. They have been doing a lot of CXL technology development and product marketing. So today's topic is about memory sharing. So I'm going to kind of first outline, from the past 3 years from what I have been working with the customers, what kind of application, that fit into this CXL memory pooling and sharing. So first, we have this called in-memory database application. And this in-memory database nowadays become really huge because, we're used to all this e-commerce and also the huge database running all the financial, all the government, everything, right? And the performance required these data to be immediately available means they need to be in the memory. The CXL provide a load and store kind of operation mode, which is much more efficient than, let's say, RDMA, which move the data around, copy data from one place to another place, and so on, right? So in the past 2-3 years, we have been working with Alibaba, which is a big cloud service provider in China. So they have done a lot of research. They have done a lot of testing development to use CXL memory pool for their in-memory database. So Alibaba this year, they published a paper which is going to be presented later this month in Berlin, SIGMOD. So that paper kind of detailed all the implementation study and the data which they did for their in-memory database. So I will give you a slide, just a pre-peek, but the full paper should be available later this month. So overall, they basically see across the board with the CXL memory pool, compared with the RDMA approach, there are a minimum 3x performance improvements almost on every category of the performance benchmark. Of course, Samsung and MemVerge, another startup in the Valley, they have done more studies, and they also showed a huge performance improvement for the memory sharing. So they overall see the 60% higher throughput and a 40% lower kind of latency for the in-memory database benchmark tested. Then another emerging application for memory sharing, that would be the AI application, AI workload. So AI have been exploding. I think people heard that in the future when AI really becomes the main application, 90% or more than 90% would be AI inference. But AI inference to be really good performance and to supply everybody's need have to be going to be cheap and going to be available, going to be really good performance. And the AI model, they are not small. They normally already gone to like terabyte, but they're going to be multiple terabyte in the future. So where these memory come from, and where do you use the bigger memory to build a KV caching and other mechanism that allow this AI workload to run efficiently? This CXL memory pool and the CXL memory sharing would be the answer. So because the CXL memory, as far as we can already see today, they are 10 terabytes, they are going to 100 terabytes, they are going to be petabytes in the near future, right? Then the other application, which the previous speaker already mentioned, both Neil and already mentioned the TCO, right? So I wouldn't want to spend more time on that, but the TCO for the CXL memory pool and the sharing was the original idea, and still that's the best idea for the data center and AI computing. Okay, so now I give you some show some data that from Alibaba Cloud, where they use this CXL memory pool and sharing for the in-memory database. They use that for their database called the PolarDB. So the PolarDB running multiple instances, but all these instances, they fetch the data from the common CXL memory pool. So this CXL memory pool are actually, data being shared. So it's really about CXL memory sharing. So in the Sigma paper, they publish on some data. So those are some data listed here, but you can see in the detail based on the throughput, based on the latency, and other benchmark. Across the board, there's huge improvement for CXL memory sharing over the RDMA system. So this paper got the best industrial award paper for the Sigma, which is going to be presented later this month. Okay, so I think I want to be a little bit of future looking. So on our next generation product, XConn, we are going to introduce a new feature, which we call the Ultra I/O latent transformer. So this Ultra I/O transformer technology going to allow the further usage of CXL memory sharing and the pooling for the AI workload. So as you see in this picture, so the traditional kind of CPU-based memory going to be the GPU-centric computing kind of architecture. In this architecture, the CXL memory can play a key role in this kind of setup because our switch will provide a transformer mechanism to allow all these GPUs, DPUs, which don't have CXL interface, but they all have PCIe interface. So our switch will be able to transform this PCIe-based memory access directly. I use the term directly means they just don't need to go through the CPU. They just directly go through the CXL switch, we call the hybrid switch, which is the XConn's pioneer technology, to be able to tap into this huge 10 terabyte or 100 terabyte memory to service these kind of AI workload, which is very demanding. So that we have a lot of detail already presented to the public, but you're welcome to reach out to XConn and me for this technology and more information about it. Thank you. So I will turn to the next speaker, to Micron.
Thank you, Jianping. Hello, everyone. Good morning and good evening. I am Arvind. I am here from Micron Technologies, and today I'm going to talk about CXL switch-based memory sharing using FAMFS and RocksDB. My previous speakers have touched upon what CXL memory sharing and pooling are all about, and given this session's time constraint, I will not elaborate on them. CXL hardware specifications have enabled us to share memory across systems, hosts. And this unlocks the potential to solve a lot of problems in a more power efficient, memory efficient, price efficient ways. So now we have heard a lot of people talk about how CXL can solve a lot of problems, but one might wonder what are these problems and how does the proposed solutions look like, and how would one visualize such solutions? um, and finally worry that maybe it's all just in theory, like what's happening in the in practice. But I think this webinar is doing an excellent job of showcasing the CXL memory sharing use cases with respect to how the problems look like and how the solutions look like. So, as I said earlier, I am going to talk about how we use it, CXL shared memory to run RocksDB workloads, and also so far we have heard about all the hardware advancements and how the hardware looks, how the configuration looks. I am going to talk a little bit more about within the system, like how once the memory is available in a system, the shared memory is available in the system. How are we going to use it? How is the system going to consume it in a efficient and a easy, much more adaptable way. So I'm going to talk about methods of consuming CXL shared memory once it's available in the system, and FAMFS, what is it, why is it, and RocksDB workloads that we ran, our observations, and some of the challenges. So um, coming to the methods of consuming shared memory, typically within a system, the system memory, we use IPC mechanisms to share the system memory across processes. And this is coordinated on the same set of processors, and cache coherency is maintained within the system. It's not an issue. But when memory is shared across systems, like in CXL, there are no well-established methods to access memory as of today. There are some methods, yes. And one more thing is that CXL shared memory should manifest as a DAX device in the system, in DevDAX mode to be consumed, because memory can be online as a system RAM mode, and that cannot be shared. So once it is available in a DevDAX mode, applications could do a mmap on the DAX device and map the memory from the DAX device, which is the shared memory, into their applications process address space, directly accessing the shared memory, the contents of the shared memory, the data in the shared memory. But it is expected to the application is expected to know the exact offsets of the data on that memory, and also the mapping and unmapping of the of those pages, and do low level memory management, or it may have to map the entire device into their address space. And if the memory is like in terabytes or hundreds of terabytes, it doesn't make sense to map that much memory into the process address space. uh, and also another thing is, to do all this, the applications need to be modified. We need to change the code of the application, um, to do this maps and unmaps, and manage this memory available to that application. And there are other options like the open sh mem framework. It's a library to share memory across systems, but again, it is also not very straightforward, and it comes with a certain overhead of its own. And coming to my first slide, given the challenges with accessing shared memory, which I just mentioned, Micron presents FAMFS, which stands for Fabric Attached Memory File System, and it is developed by John Groves, and it is open source. And I am also an active contributor to the project. It's available on GitHub, so please please check it out. FAMFS. Uh, uh, I will not go into the internal details of the FAMFS because of the time constraint. A lot of stuff is available on YouTube and GitHub. You can kind of ping me or John for more info if you need. FAMFS basically provides a file interface to the data in shared memory. So now we have all the switches and CXL memory modules behind the switches and everything we have, and that memory is available to different hosts. But like, how do these hosts consume that memory? Uh, so FAMFS provides a file interface to the data in that shared memory. If you can put the data in as a file in that shared memory, and if applications can read write to any file system, which almost all of them do, and then they can use FAMFS to consume data from a CXL shared memory as files. And this is scalable in the sense that more memory can be added to increase the shared memory size, and also more hosts can be added or removed as needed. And no modification is needed for applications to use the uh, and no modification is needed for applications to use the shared memory. They can do it out of the box with FAMFS. FAMFS expects the shared memory as a DAX device in DevDAX mode. And once that is available in DevDAX mode, it can do a format file system on that device, and it can read or write from that shared memory. So we wanted to show this that data share that the data in this shared memory can be consumed as files, which has the potential to enable a lot of use cases. One such use case is RocksDB, and we want to show that. So this slide shows FAMFS that it organizes memory as a file system, and one shared memory can be accessed by multiple FAMFS nodes, and one of those nodes is a master node where the formatting of that file system happens. But all the client nodes have access to the shared memory and can read from the shared memory. So let me go to the next slide. So here, let me explain the hardware setup that we used. Here we have a CXL switch, which was from XConn Technologies, and which is connected to N Micron CXL memory modules. CXL memory modules are nothing but modules with memory within them, and these CXL memory modules are connected to the backplane of the switch, and the switch front end is connected to hosts via the host PCIe ports. So in this case, we had more than 12 CXL modules amounting to up to, I think, around 1.5 terabytes of shared memory accessible to all the hosts which were connected to the switch. So in one of the nodes, we formatted the shared memory into FAMFS file system. And then we used RocksDB, which is a key value store, to create a huge database in that FAMFS file system. Now, this RocksDB database was accessible from all other hosts which were connected to the switch, and also given that the switch and memory modules were based on CXL 2.0 spec, it was not cache coherent. So we could not modify the database concurrently from all the involved hosts. So we kind of ran parallel read-only workloads from the hosts, which circumvented the cache coherency problem, and that is until we have CXL 3.0 compliant hardware, which solves the cache coherency problem, and I'm sure is on the way. So now with the host bandwidth bound by the PCIe bandwidth, that is, each host has a PCIe bandwidth, and that bandwidth, even with PCIe Gen 6, is much lesser than DDR5 bandwidth available within a single CMM, that is CXL memory module, and it can be a source of bottleneck. So when a CMM is directly attached, bottleneck when a CMM is directly attached to the host. However, with a switch, the available bandwidth is much higher, and many hosts can access the same backend bandwidth, and while saturating its internal host bandwidth, and it can be beneficial for certain workloads. So in this case, each host was able to saturate its PCIe bandwidth while allowing to add more hosts and continue to access the same database. Yeah, and here I want to talk about one more experiment that we did. So here we compared read operations per second when the entire database was in FAMFS versus when the database was in an SSD, but fully cached in system memory. So the database, let's say, was of size 100 GB. It was in FAMFS, and the same database was on an SSD, but it was fully cached in the system memory. Um, and we gradually increased the database size from less than the memory size, system memory size, to almost 2x of the system memory size. So when the database size was more than memory size, only part of the DB was cached in system memory, whereas in FAMFS and shared memory, the entire database was available at memory speed. Uh, so because of cache misses, when the database size increased, the performance dropped. The and performance and the latency kind of were very badly affected. Uh, and this was not the case for FMFS, as the entire database was in shared memory. This also kind of shows a use case where a single system cannot handle the size of large databases, and we use shared memory with FAMFS and memory sharing to deliver more ops per second. And like I mentioned earlier, it allows to scale up the number of hosts reading from the same memory and also to increase the memory size in the backend. So as a conclusion, I would like to highlight FAMFS, Fabric Attached Memory File System, as a key enabler of open source software, which can drive CXL shared memory usage and also adoption in the coming days. So I'm open for questions later, and thank you all for listening in. Thank you.
Thanks, Arvind. I'm going to take over at this point. Hello, everyone. My name is Sandeep. I'm part of the product management team here at Astera Labs, responsible for our CXL product line. I'm also a member of the CXL marketing working group. So to begin with, before I jump into how we have been able to take CXL memory sharing from being concept to real world use case, I wanted to briefly talk about what's driving the need for CXL based memory sharing use case, since memory sharing, as Anil pointed out earlier, is not a new concept in data centers. I've listed on the left-hand side some of the limitations that are currently inherent in the existing memory sharing use case. Let's start with the scaling factor. Evidently, as the AI and data center scale increases significantly, we need to look at a more efficient implementation, since implementations such as interprocessor communication, which is predominantly how memory sharing is done these days, is not performant. In other words, it is high in latency, and this is critical as we scale the data centers. Secondly, we still have over-provisioned memory in data centers, which leads to unused or what's known as stranded memory. And this is particularly relevant in multi-tenant platforms. And all this leads to higher TCO, which diminishes the value of sharing memory in the first place. So when we look at the benefits of CXL-based memory sharing, which is what I'm pointing out on the right-hand side, this solves some of the problems that I highlighted on the left-hand side, in that we can provide a very efficient resource utilization methodology versus what's currently implemented. At a spec level, it is designed to reduce over-provisioning and stranding of memory. Performance-wise, it has been proven to be as efficient as 4x lower latency compared to the traditional remote procedure calls. And last but not least, VM level resilience is supported through CXL, TSP, and IDE type of features. In fact, TSP was architected for exactly this purpose, in that you want to provide isolation when you implement pooling and sharing type of use cases. So we can leverage all the standard-based methodology for achieving that. And you can see that that level of resilience is not something that is implemented in the current memory sharing implementations. Let's move on to the next slide. Now let's look at how we've been able to take CXL-based memory sharing from concept to reality. Because it's one thing to put things on paper, it looks really shiny, but we want to make this happen in real world. And that's exactly what Astera Labs Leo Smart Memory Controller can or is able to achieve. It is unique in that it supports bifurcation to 2 by 8, thereby supporting sharing and pooling along with the typical memory expansion use case, which is what the block diagram on the top left-hand side shows, where each of the CPUs can access the shared memory behind Leo. And since this is just one hop away, we can maintain one NUMA hop latency, which is quite critical for the end applications in data center. If you look at the lower half of the block diagram, it shows a topology that has been implemented with Leo, where multiple hosts can share the memory behind the memory controller. In this representative use case, we have two hosts sharing the memory controller. In reality, you can expand this to a significantly larger topology. But the key aspect here is, as shown in the table on the right-hand side, this implementation is meant to actually productize the use case. And there are several aspects we need to take into consideration and not just being able to expose the memory. What I mean by that is Leo has all the hardware, firmware, and software features that takes into account uh, factors such as interoperating with multiple hosts. More importantly, being able to handle link up and link down events gracefully, maintaining resilience across reset events. For example, if one of the hosts goes down unexpectedly, it should not affect the other active link. Similarly, RAS telemetry and management from each host is also quite important in data centers because you want to maintain the same level of resilience that are currently inherent in the data center environment. And when you introduce a new technology like CXL, you don't want to compromise on the quality of the product or the resilience of the platform itself. So in a memory sharing environment, since you have multiple hosts, it becomes even more critical to maintain RAS. Last but not least, software layer, which we have branded as Cosmos, which stands for Connectivity System Management and Optimization Software, provides easy to use manageability framework that is designed based on standard-based methods. I will explain a little more about this in the next slide. But the key takeaway from this slide is to be able to productize a memory sharing use case, you need to take into consideration all the factors that I've highlighted here in the table. And we are capable of supporting all these features, and in fact has been put into practice with the representative application that I showed in the bottom left-hand corner. Let me move to the next slide to expand a little more on the efficacy of the software stack as well as how we can support it. Going one level deeper with this Cosmos slide, as I said, it is a combination of firmware and software that is designed to do link management, fleet management, support all the RAS and security management aspects of it. And as I said, this is based on standards such as CXL, DMTF, and all the leading security standards as well, which means that your platform management framework can leverage existing implementation. To expand a little more on what I mean by that is, we support all the CXL CCI framework, as you can see from the right-hand side, using standard primary and secondary mailbox interface. On the left side, you can see how we have implemented MCTP, PLDM for platform monitoring, and SPDM for security. And this is all based on DMTF standard. So the takeaway here is that in the data centers, we can rely on standard-based methods. So it cuts down the time to production since you don't need to reinvent the wheel and use the existing management framework. And this is really key for us to productize this, to have a common management framework that's based on standards. That way the designers don't need to reinvent the wheel, as I mentioned earlier. In summary, as my co-presenters made a strong case for memory sharing, cloud and AI demand is driving a very strong need for memory sharing. The legacy solutions that have been implemented so far are inefficient in that it is lower in performance, high TCO, as well as the software complexity portion of it is what prohibits us from being able to scale this as we move forward towards next generation data centers and AI applications. So CXL-based memory sharing addresses these needs in that we can provide an efficient method for utilizing the memory between multiple hosts, which provides lower TCO for better performance as well as better security. And at a spec level, we have all the plumbing needed to enable memory sharing between multiple hosts and peer devices. Astera Labs Leo Smart Memory Controller enables this because it's purpose built for pooling and sharing kind of applications for data centers. And I would encourage the audience to download the latest CXL 3.2 spec for more details on how this can be implemented, particularly the fabric management aspect of it, which is tailored for pooling and sharing type of applications. Thank you. With that, we can open up for any questions from the audience.
Thank you. We will now begin the Q&A portion of the webinar. So please share your questions in the question box. To start with, I want to share what are the effects of noise neighbor in memory sharing?
I can take that. Noisy neighbor effect comes into play when you have multiple hosts trying to access a common device. Even if there is bifurcated into different links, whether it's by 4 or by 8, the concern there is from performance standpoint, one link might interfere with the other link's performance. Now, the answer to this is whether it's memory controller or switch, as long as you're maintaining QoS or quality of service across the links from individual hosts and have some kind of an arbitration or a round, say, for example, round robin scheme for allocating slots for individual links and maintain proper flow control mechanism, you will be able to avoid noisy neighbor effect. As far as the shared memory resource is concerned, that is all managed by the device itself, whether it's memory controller or the switch based on the HDM decoder address allocation. So the takeaway here is you need to have proper arbitration and flow control mechanism to maintain bandwidth and latency and avoid noisy neighbor effect.
Thank you. In a shared memory architecture, how do we manage telemetry and security across multiple hosts?
Again, a very good question. And this goes back to what I was emphasizing in a couple of slides I was sharing earlier. Typically, in a data center environment, you would have a centralized BMC, which collects all the telemetry logs so that the fabric management software can monitor all the events as well as notifications. And this is all typically done via out-of-band interface, which could be I2C or I3C. Now, that doesn't mean that the host cannot access telemetry by itself. That is also something that we can provision through in-band interface. And this can be useful in ensuring that that the hosts are aware of the state of the memory that each of them are accessing. Now, security is a different aspect altogether. As far as that is concerned, it is really the responsibility of the memory controller to support features such as CXL Link IDE, secure boot, and if we talk about TSP, then it would be the host application's responsibility to ensure that at a VM level, you maintain the trusted and untrusted states for a given address range. And the memory controller would just honor that. And this is all done via a standard in-band interface or CXL interface. And this, in fact, is in the CXL 3.0 spec, quite well defined.
This is Oren from UnfabriX. I think that we need to elaborate on both questions. So first of all, regarding the noisy neighbor, In memory sharing, there is a challenge because you have 8 hosts trying to address the same memory space. So beyond control mechanism, it may create some effects that will increase the latency, for example, and may reduce the throughput. So we are implementing mechanism for data striping because if you are trying the same to address the same memory module with 8 hosts, it can create bottlenecks. While using multiple memory modules at the same time, you can actually improve the latency and make sure that you are reducing all the effects between the different hosts. So implementing those mechanisms may improve the noisy neighbor and actually eliminate it totally. So it's something to notice, and each application will have its own experience while doing it. Next question.
All right. With the Ultra I/O transformer, what is the way GPUs will access memory? Is it a load store or some other mechanism? Since it is a PCIe device, it will not be coherent shared access. Is this correct?
Yes, so this is JP from XConn. So for the Ultra I/O transformer, the GPU, their PCIe space, they are just normally through this DMA mechanism to access the PCIe MMIL space. The switch make the transform basically, bridge the PCIe to the CXL without the GPU or the DPU to be aware there is a CXL. So we implemented this technology in a way that doesn't need to make all the changes to the existing hardware.
Thank you, GP. For using max memory as memory sharing, what is the access latency if we want to access the same object cache coherently?
Okay, so again, this is a very interesting discussion about latencies. You have seen the latencies in the max memory. We are way below 500, and we are behaving like a memory module, so in the range of 400 and below that. But I think that the discussion about latency in memory sharing is not the right question. It's also about bandwidth. As we discussed before in the discussion about noisy neighbor. For example, in our system, we are able to create bonding. It means that we can connect multiple CXL link and go beyond by 16. So today it's a Gen 5 by 16. We are able to do multiple links, so you can do like by 32 and even more than that, and actually solve any latency or bandwidth limitation that are in the systems. Next question.
All right, thank you, Oren. So how can CXL memory sharing be used in AI workloads?
So, Elsa, I'll take answer to this. I think today's CXL 2.0 system can already take advantage of CXL memory sharing, but they do it through the CPU because all the GPUs they don't have the CXL interface. So that's we already see some early study by Micron, by Memverge, where they run the AI workload to access this huge, CXL memory pool. In the future, XConn outlined the Ultra I/O transformer technology. We would enable all these GPUs to directly access the huge CXL memory pool to do the AI workload. And today, some of the database is, called a vector database can already run this AI workload. And these vector database, which is one form of the in-memory database, they already can use the CXL memory.
All right. Well, thank you, Oren, Arvin, Anil, Sandeep, and JP for sharing your expertise. We will address all the questions we received today in a future blog, so please follow the CXL Consortium on our social media channels for updates. Thank you for attending the CXL Consortium webinar. The presentation recording will be available on CXL Consortium's YouTube channel, and the slides will be available on our website. We want to encourage our viewers who are not members of the consortium but interested to learn more about CXL to join the CXL Consortium. Our membership information is available on our website. Thank you, and I hope you have a great day. Bye.